As I mentioned, kind of introducing Nilanjan, I'm basically just part of the audience for this conference. I try to find people that I like listening to, who I think I can learn from. Obviously, Nilanjan was no exception. Next up, we have Raju Gandhi. Raju, I've somehow managed to not work with, despite me trying to get him to work with me for the last 10 years. He's avoided me every time. But he's a really smart cat. Maybe that's why he's a really smart guy, so he's not working with me. He's loosely typed on Twitter, but he's here to talk to us about Gittin Git. So help me welcome Raju Gandhi.
Thank you. So can everyone hear me OK? Awesome. Well, let me start by saying that this is my first time at this conference, and everything I've seen so far has been very impressive. So I think as a show of appreciation towards the organizers, I know Todd pulled me in to speak at this conference, so thank you, Todd. Hopefully, all of you will get out as much as I think I will out of this conference. With that said, I know Nilanjan had the keynote. We are going to talk about Git today. And specifically, we are going to look at the internals of Git. So how many people in this room have used Git? How many Git users? Even played with it? You have it installed on your machine. Good. So lots of Git users. Now, I know Todd already introduced me. So I'm Raju, and I'm loosely typed on Twitter. And for most of my technical talks, I usually have two disclaimers. The first one is that I get excited, and I start to speak really, really fast. If you have any Indian friends, you might have noticed this phenomena at work. Right? We start to speak really fast, and you have no clue. That's right. We got Venkat up here who's quite enthusiastic when he's speaking. The second one is very subtle. Now, this is usually not a problem. But the two in combination are lethal. Right? So if you don't understand something, just raise your hand. Hopefully, I can catch you behind the glare of these lights. But feel free to ask questions anytime. Feel free to ask for clarifications anytime. Is everyone good? Get started? All right. When you think about Git, most people approach it as a source control system. But Git is beyond that. Git, in my opinion, is going to contest with Linux as probably one of the most influential pieces of software Linus has written. And I know most people think Linux is far more important than Git. I have a feeling that 15 years from now, we are going to be thinking that Git is probably his most influential piece of software. So when you think about Git, I don't like to think of Git as a source control system. I like to think of it as a great lesson in software design. Once you understand how Git is written from the ground up, you really learn how to make great software. And that's what got me interested in Git, or the internals of Git. This is what Linus has to say about understanding the internals. Right? We are developers. We should always understand one level of abstraction below the level at which we work. Right? If you use Hibernate, you should know SQL. Right? That goes without saying. Now, for all those who've used Git, how many of you have looked inside the .git directory? Anyone? Few of you are curious. Well, before we start, let me do this. Can everyone read that font, or is it too small? People in the back, especially. Is it good? OK. So I have here a directory that's completely empty. And I apologize for that, but it's an empty directory. What I'm going to do is I'm going to git init in here. And so what I just did is I initialized a brand new Git repository in that directory. Let's take a look and see. So if I look inside the Git directory, you see a couple of things, right? You see head. You see a bunch of hooks. You see refs and objects. And this is what we're going to look at today. We're going to see where the magic is inside Git, right? This is what I just showed you. This is the directory structure under the .git directory. Everything that you see in orange is a directory. Everything in gray, sorry, everything in orange is a directory. Everything in gray is a file. We're going to focus on 3 parts of this. We're going to look at what the head is all about. We're going to see what the object database is. We're going to see what the references are. Does that make sense? Awesome. Now, at its very core, Git is only made up of 4 constructs, 4 simple constructs. Once you understand the 4 constructs, you are on your way to Git mastery. A blob, a tree, a commit, and a tag. And for today's discussion, we can skip off tags because they are just glorified branches. So it doesn't matter. We're going to look at blobs, trees, and commits. Now, what's a blob? A blob in Git stores the contents of your source code. Of any file in Git, the contents are stored in a blob. Now, right off the bat, you might notice that this is different from other source control systems. Git does not store files. Git stores the contents of a file. Git uses the SHA-1 hash of the contents to figure out where to put it and where to retrieve it from. So how many people know what a SHA-1 hash is? Raise your hands. So what is a SHA-1 hash? The one in the gray over there, right in the middle. Yeah, you. Your neighbor's looking at you. Yep. It's an encryption algorithm. Essentially, what it does, it takes a bunch of content, any string, and produces a 40-character string out of it. You can give the SHA-1 algorithm 2 kilobytes of string or 200 megabytes. It will still produce only 40 characters that uniquely represent that string, which means that 2 different strings will have, for the most part, 2 different SHAs. There is a chance of collision, but that we can ignore for now. That probability is 1 in 10 billion, or something to that effect. So if I give a SHA-1 algorithm 2 pieces of content, it will generate 2 unique SHAs to represent it. Now, how does Git use this? So what we're going to do is, I've lost my way here. OK. Right over here, I'm going to say echo hello Columbus and pipe it to a function that Git gives us. I'm going to say echo this string and pipe it to Git's hash function. Let's see what it produces. And we get a SHA out of it. So this is the SHA that Git will use to store the content, hello Columbus. Does that make sense? Now, where does this go? So what I'm going to do is I'm going to do the exact same thing. Here, let me start this real quick. OK, all I have on the right side is a loop in bash that refreshes that screen every 1 second. So you can see what's happening under the covers in the Git directory. Over here, I'm going to do the same thing, except this time, I'm going to pipe it to a README file. So now, in my working directory, I have a README file. And I'm going to add the README file to Git. Now, let me just do this real quick. So we have the sharp here. And now, let me add this real quick. So git add. Now, I want you to watch this right here, the objects directory. Uh-oh. That didn't work very well. There you go. So under the objects directory, we now see a new directory called 3b. Under that, we see some file called 58078. Let's look at the other side. The SHA that was produced out of Hello Columbus was 3b580782. So what did Git do? Git took the contents of the README file, calculated the SHA, then made a directory with the first 2 characters of the SHA under the objects directory, made a file with the rest 38 characters, and stuck it inside there. Does that make sense? Now, the next question you might have is, what's the content of this file? This is the blob. What this has is the string hello Columbus zipped up. So it takes the content, zips it up, and puts it in that file. This is also the reason why Git is referred to as a content addressable file system. The contents describe where they will be stored in the file system. Everyone with me so far? Any questions? Yes, sir. That is a good question. So the question over there is, if you have a file, how do the file names get addressed, right? Because we're talking only about the contents over here, and that's actually very astute. We'll come to that in 1 second. And if I don't answer your question in the next 3 minutes, let me know. So that is an astute point, is where does the name of the file go, right? Well, we just saw this happening. And we know that our content is now safe inside Git. The question is, where does the file name go? Well, the blobs have no metadata. There is no file name. There is no file type. There is no file permission. There is no file path. In order to store that, Git uses yet another kind of object called the tree. And by the way, I've got these funky icons on the top. So those represent those. When I visualize this, use those. So a blob is a blue rectangle, and a tree is a triangle. The tree stores the structure of your working directory. It stores the names of the files and the paths of those files. So over here, I can say, hey, Git, write the current tree. What does the current tree look like? It's one file, right? You have the root directory and a README file underneath that, right? Git gives us another SHA, C3473A. At the same time, it created a folder called C3 under the same objects directory and made a file with the name 473A blah, blah, blah. So now the question might be, what's in this file? Right? We can ask Git that. We can say, hey, Git, tell me what this SHA is. So Git says the line that's stored in this file looks like this: 100,644 space blob space 3b blah 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 tab readme. What Git did is it took this string and created a SHA out of that. Does that make sense? What is this SHA? Where did we see 3b580 before this? It's the SHA of the blob that was created. So earlier, we had the blob, which had the contents hello Columbus. That was stored in a file called readme. What Git does, it now writes out a single string, which is, this is basically your Unix file permission, 644. It writes the word blob. It writes the SHA of that blob. It writes the file name of that blob, takes this entire string, and SHAs it up to create the SHA of the tree. Does that make sense? So now if I had two files in the working directory, what would Git have done? Git will have written two lines. And I can show it to you right here. This is a simple structure. This is a slightly more elaborate structure. I might have a subdirectory inside the working directory. If a subdirectory exists, the subdirectory itself is a tree whose SHA is calculated by the blobs that it contains. Then Git takes that tree SHA and any files it contains, takes this entire string and SHAs it up to calculate the SHA of the root tree. Does that make sense? How's everyone doing? Any questions? Did I answer your question, by the way? There's someone in the corner. Everyone good? It sounds like a lot of work. Well, we don't have to do it, right? The point here is that the file contents define where they'll be stored in the objects directory. The very same SHAs define the SHA of the tree they are contained in, right? So if I change the contents of README from hello Columbus to hello Chicago, the file name remains the same, but this SHA will change because the contents have changed. And that cascades up. Does that make sense now? It recalculates the SHAs of that blob and every tree above it, all the way to the root. There is an advantage. And we'll come to that in a few minutes. So this number that you see, 100644, that is for a regular text file. You can have something for a tree which is 040000, which doesn't mean anything in the Unix world. It's just a way for Git to represent a tree. You can have commits. You can have codes for symbolic links, because Git has to manage symbolic links differently than it manages regular files. So the way you can visualize this is the root tree SHA is a function of the SHAs of the blobs right beneath it and of all the trees that it contains. So if your root directory had a source, a test, and a README file, the root directory SHA is the SHA of the README file, It then goes to calculate the SHAs of each tree. So it goes down source all the way down, calculates the SHAs up, goes down test, calculates the SHAs up, and uses the 3 SHAs to calculate the SHA of the root tree. Yes, sir?
It sounds as though ordering would be very important here.
That is correct. So the ordering is alphabetical directory structures. Now, that's also the same reason why Git is case sensitive when it comes to file names. So if you ever used a Unix system and a Mac system, and Unix is case sensitive, right? So readme uppercase and readme lowercase are 2 different files. You try and shove that Git repository on a Mac system, and Git will choke. Because it tries to write the same file twice, and it chokes because Git Mac OS X says, readme seems the same to me. That's why it chokes. But you're right, the ordering does matter because you change the contents of the tree around and the SHA changes. Yes. So that's the blob and the tree. Now we're going to talk about our good friend, the commit. This is the level of abstraction we work at. This is the only thing most Git users care about, which is the only thing you need to care about. The commit is the level of abstraction that Git will expose to you. A commit references a tree, 0 to n parents, author info and timestamp, committer info and timestamp. That's basically your author info, and then a commit message body. So let's take a quick look and do something over here. So what I have to do in this case, because I've completely mucked up my Git tree, I'm going to do, really, now? Remind me later. Actually, never remind me. I'm going to blow away my Git directory. And I'm going to start again. So git init, git add readme. OK, and we're going to run this guy. Oh, come on. And I'm going to this time do a git commit with some message, my first commit. So you can see up here, we have the 3b that we had last time. We have the C3, which we had last time. We have one more, 9E36, which is basically the SHA of the commit that Git reports to you, 9E36. So the question now is, how did 9E36 get calculated? And what's in this file? Right? So let's ask Git. I'm going to say, hey, Git, what does this SHA, let me do this. So you can see this better. Git cat file -b. These are this is the content of that file under .git/objects. It has a line which says tree space C347. Where did the C347 come from? That is the SHA of the tree, the root tree. There's author info, there's committer info, there's a blank line, and then there is the commit message. Git takes this string, SHAs it up to create this SHA. It takes this string, zips it up, and puts it in that file. Make sense? That's your commit. That's it. There is nothing more to a commit in Git. All right. So we just saw this. We have a commit that basically has this string. In our case, we don't have a parent because this is our first commit. We'll talk about that in a few minutes. But this string shard up creates the SHA of the commit. Now, if I change the contents of the README file and I make another commit, what changes? Git takes the new contents and calculates a new blob. That blob affects its tree. That tree is inserted here. So the SHA of the next commit will be different than the one of the previous commit. Let's say I didn't change anything, and I force Git to make a brand new commit. Will the SHA of the next commit be different than this one? How many people say yes? It will be different. How many people think no, it won't be different? All those who said yes get an extra half cookie at lunch. Timestamp will change. When I commit the first time and I change nothing and I commit again, this timestamp will change, which means this string will change, which means I get a brand new commit. What's interesting about this is that every repository in the world, every commit in every repository in the world has a unique SHA, which is really cool when you think about it, right? 40 characters can be a lot of numbers. Hopefully, we don't run out anytime soon. This is the structure we are looking at. You may have an initial commit. When you make a second commit, that commit has a pointer to the parent SHA, like you see in this case. This parent that you see, this SHA, is the SHA of this commit in this guy. His child points to him. Each commit points to a tree, which is the root directory. That root directory points to all of the blobs directly underneath it and any subdirectories that point to the blobs underneath it. How's everyone doing so far? Good? Now I have, depending on your perspective, good news or bad news. Every time you commit, Git takes the entire working directory and stores it in the commit. Which at this point you're thinking, this guy is crazy. I didn't pay good money to come here and listen to this lunatic talk, right? Think about it. How old is the Linux project? Now about 22, 24 years. And I'm saying that every commit has the entire working directory stored in it. There are tens of thousands of commits on the Git repository of Linux, and each one stores the entire working tree. This is where Git is different from a lot of other source control systems you've used. Because what do most other source control systems store? Deltas. They store deltas between files. When you change a file, they just calculate what changed and store the change. Git says, you change the file, I'm going to just save the whole file again. Which is really nice, because if you are on the 10,000th commit and you want to compare it with the second commit, what does Git do? It takes the file, the contents of the file that you want to compare from the 10,000 commit, takes the contents of the file from the second commit, and diffs those two. It doesn't have to go through 10,000 commits to figure out what changed. It can take two absolute versions and diff them, which is why diffing is so fast in Git, because Git has no calculation to do. It goes to that blob, reads the contents out, goes to the other blob, reads the contents out, side by side. Done. Now, of course, the question you have is, how does it store it? Well, let's take a look. Let's say we started with an empty commit, made a file called readme, just like we did earlier. Hello, Columbus. At this point, and I don't know if you can see that behind this, but basically I make a new directory, I add and I touch a new file, and I commit a new file. What does Git do? My contention is that this file will get stored again in the next commit. Now remember, I haven't changed the file, but it will still get stored. What does Git do? Git creates the next commit to look like this. Remember, the SHA can only change if the contents change. If the contents of the README file don't change, Git can reuse the SHA. So this commit has the entire working directory inside it. The fact that this guy gets reused, it's not a problem. This is also referred to as, in loose terms, persistent data structures. Any Clojure users in the room? You can't raise your hand. Any Clojure users in the room? This is how Clojure persistent data structures work, right? They just copy over whatever they can and only create additional items or remove additional items. So the thing to take away from here is a couple of things. But the most important one is a commit in Git is not a delta. It is the state of the working directory at a particular point in time. We know the time because it's recorded in the commit. We know who made the commit because it's recorded in the commit. We know the state of the working tree because we have a tree pointer. That tree pointer points to blobs and other trees. And we can recreate the entire directory structure by looking at a commit. Which means, let me just go back here real quick. Let's say there was a way for us to throw away this commit and say, reset me to this guy. What do you think Git does under the covers? Can anyone take a guess? Git goes to your working directory. I'm glossing over some details here. But essentially, it deletes everything in that working directory. Then it goes to this commit and says, what does your tree look like? And that tree says, I have one file inside me called readme. It creates a file called readme. Then it goes to that blob, unzips the blob, reads the contents out, slaps it in that file. Done. Which means a Git reset is essentially replay this commit for me and recreate this directory structure. That's a reset, essentially. There's nothing more to it. Because I have the entire state of the working directory in every commit, when you check out branches, what happens? Same thing. When you switch branches, Git throws away the working directory, goes to the other commit, replays the entire commit on the file system. Does that make sense? So we just spoke about branches. How many people love branching in Git? Just one hand? That's what Git is all about. If you don't branch in Git, then you should go back to Subversion or CVS. I was at a client where we literally had to do the rain dance, take the CVS admin out to lunch so we could get a new branch created. I'm kidding about the lunch, but it was quite the dance. Branching in Git is extremely cheap, and you should be branching all the time. The question then comes is, how is branching so cheap? A branch in Git is simply a named reference to a commit. Now, I don't know about you guys, but does anyone remember that 40-character string that represented Hello Columbus? Anyone in the room? Remember all 40 digits? You sure? Because if we could, we won't need branching in Git. As long as we could remember 40 characters of the blobs and the trees and the commits, we would be golden. The reason Git gives us these branches is because it says, I pity you. Since you don't remember it, I will give you a humane way to reference a SHA, a 40-character SHA of a commit. So what I'm going to do here, notice there's this file over here, reference heads master. I wonder what that guy is all about. Let's do a git log real quick and see where we stand. We have a SHA. We have an initial commit 9E36ACA blah, blah, blah. That's our latest commit on master. I'm going to do a less on.git refs heads master. And it has inside it, does everyone know what less does? Basically, I'm just reading the file, just catting the file. It has a SHA in it, 9E36ACA. So the master file has a SHA in it. Now what I'm going to do is I'm going to create a new branch. Some branch. Please don't name your branches like this. And if you do, we've never met. Git branch, some branch. I'm going to create a new branch. Keep an eye and see what happens over here. Now there's a new file called some branch. Can anyone guess as to what the contents of that file will be? It will be this SHA. What SHA will it be? The master SHA, right? So now I have two files that have the same SHA in it. Now, let me just make a commit over here. So let me check out, so git checkout some branch. So now I've switched to that branch. And now I'm going to do just force a commit. So allow empty -m on some branch. So Git created a new SHA for us. If I were to see the Git log, you notice that some branch has 154, whereas master is on 9E36. Can anyone take a guess what this file contains now? Both SHAs? Just one SHA, the SHA that you are on right now. 15DD, blah, blah, blah. So the way you think about branching in Git is you think about it as a post-it note. That's the way I like to think about it. It's a post-it note with a SHA in it. So whenever you have this situation, right now this post-it note contains the SHA of this commit inside it. If I were to do a git checkout, a new branch, new feature branch, what Git does, it goes to its post-it note, writes new feature on it, then looks at the commit you are at, and writes that commit in that post-it note. And so you get a new post-it note and a new file under the heads branch. And that's it. That's a branch. It's a post-it note with a SHA in it. Now, we already did this. On the new feature branch, if I were to make a commit, what happens? What have we learned so far? I make some changes, and I make a new commit. Let's say I touched the README file and I changed its contents. First, what happens? Anyone? A new SHA, the blob is calculated. So the blob is written out, the SHA is calculated. Then what happens? The tree's SHA is recalculated because its file name did not change, but the contents changed. Then a commit is written out, pointing to that tree with the author info and the commit message. Right? You get a dot like this. And then Git moves the post-it note up there. So it erases the previous SHA and writes the new SHA on the post-it note. And that's how it remembers what commit a branch is sitting at. Now, many of you might have used a command like git branch. What is git branch? It's a glorified ls. If I did ls.git refs heads, I get the exact same output. It's a glorified ls, with the exception that it knows this highlighting stuff, which branch you're on. It's a glorified ls. It's nothing else to, there's nothing else to it, right? So we know branches are post-it notes. I apologize for this. We know branches are post-it notes. So then what's the head all about? How does Git maintain the head? The head points to the checked out commit. Please note, I didn't say the last commit. I didn't say the current branch. I said the checked out commit. And we'll see what this means in a second. The most important attribute of the head is that it will always, 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 always be the parent of the next commit. Remember that each commit has a parent that it points to. Wherever the head is pointing will be the parent of the next commit. And we'll see that in a second. It is usually the last commit on a branch. That's how normally we work. That's not to say that that is what is the case, but that is usually how we work. So currently, Git says head points to some branch. Now, if I were to do on the Git, there's a file here called head inside the .git directory. Let's take a look and see what's inside that file. Those are the contents of the head file. It has a pointer in it. It says the current reference is refs, heads, some branch. What's in refs, heads, some branch? The SHA of the commit it's at, which means that head usually points to a post-it note. The post-it note points to a commit. Now, if I do a git checkout master, what will this contents be now? Refs, heads, master, right? No surprise there. So essentially, if this is the state of affairs, and I say git check out something, right? I say git check out new feature. Git takes this symbolic link, right? This is a symbolic link. It points to a link that points to a SHA. It merely takes that guy and says, move him over here. Now you've switched heads. You're now on a new commit. The minute you switch commits, what happens? Git wipes out your working directory, goes to this commit, looks at its tree, starts unwrapping, writing out files to the file system. Done. This is the same reason why if you have files checked out in one branch and you try and switch branches, Git says, can't do it, because it has to delete those files, and it can't delete those files without your permission. So it says, sorry, either check these files in or throw them away before I switch branches. If I do a git checkout master, Git just moves the the symbolic link back. Now, when I say git checkout master, essentially what am I doing? I'm saying git checkout the SHA that's inside master. Well, if Git can do that, I want to do that. I want to say git checkout this SHA. You think it'll work? Yes, it will work. Git moves the head there, and that is what is referred to as a detached head state. Has anyone ever seen that warning? It's pretty scary when Git does that. Yeah, I'll show it to you. OK. I'm going to say git check out this SHA. Oh, no. Oh, no. You are in detached head state. You can look around and experiment, yada, yada, yada. All it's trying to tell you is you are now what is known as an anonymous branch. The head is directly pointing to a commit instead of pointing indirectly to a commit. So any changes you make here, you will eventually lose unless you have the uncanny ability to remember 40 characters. Right? Goes back to the post-it note discussion. If you can remember 40 characters, good for you. No, not this dance again. OK. So we've understood all that. How's everyone doing? Is that making sense? Yes, sir. I'm sorry, you have multiple people checking out files, right? Well, OK. So the question is, we have multiple people checking out the same files. How do the pointers work in that case? Yes? Even different files. That's fine. Now, the one thing to bear in mind is Git is distributed, which means everything you are seeing in that tree is happening on your machine. You have your copy of a Git repository. I have my copy of a Git repository. The only thing we share is that tree of commits that we saw, which I should have mentioned. Let me go back here. This tree is called the directed acyclic graph. It's called directed because things point to each other. It's called acyclic because children point to parents, not the other way around. And it's a graph because it's got dots and arrows. Good enough. That's my data structure 101 for today, right? Anything with dots and arrows is a graph. But this is a directed acyclic graph. This is what you and I share. We share the post-it notes, the master sum feature, only if you push that post-it note up to the server. So you say git push origin some post-it note, and Git will create a copy of that post-it note up in the server, and then you and I can share the same post-it note. Now, once we get copies of the post-it note, those post-it note becomes local again. I can move that post-it note any way I want. You can move it any way you want. If both of us attempt to push, last one has to resolve any issues that come up from the pointers not being correctly set.
So the local copy then ahead refers to your last checkout.
Your last checkout.
So it's a reference in the servers agnostic.
Completely agnostic. The server has its own head pointer, because it needs to know the last time I pushed, where was the last commit. So it has an origin/head, which is different than my head and your head and everybody else's head. Yes. Yes, sir. Mm-hmm. Yep. You will have that problem because Git is file system based, not access control based. So it's not like you're logging into a system with some credentials. So the minute you check out, I mean, in fact, the same thing. If you have 2 branches, you can have only one branch checked out at one time in a Git repository, right? Which is a problem a lot of newcomers face, is I have this branch, I have that branch, I want to see both of them together. Why would you ever want to do that? I don't know, but people want to do that for some reason. So then they create 2 directories, and they check out different branches in each directory. But that's just the very nature of Git. Yes. All right, so we were talking about marriage and relocation. So completely different subject over here, because this is very personal to me. So I need your advice. I'm kidding. Let's talk about marriage and relocation, right? Marriage is merge in Git. That's how I remember it. I realize all the analogies are pretty simpleton, but I'm not the sharpest bulb on the tree. So I need simple analogies, right? So merging in Git is marriage. 2 or more commits come together to potentially create a child commit. That is a merge. So let's take a look. Now that we understand the directed acyclic graph, we can better visualize the process. I have 2 branches. What branch am I on right now? How do you know? Because the head points to master. If master asks new feature to marry him, so you are on the master branch, and you say git merge new feature, right? New feature marry me. Then what Git will do is it will create a child commit representing the merge. This is not always the case, but this is one way a merge will happen. Sometimes you get a fast forward merge, but that's a different story, right? So these 2 came together to create a child commit. Now, if you remember a few slides back, I said a commit has a tree, 0 to n parents, author info, committer info, commit message, right? 0 parents if you are the first commit in a repository, n parents if you have 2 parents. The immediate parent of this commit is the person who did the proposal. And the secondary parent will be the guy who got merged into him. Does that make sense? Now, one thing most people don't know in Git is you don't have to say git merge new feature. If I had 5 branches over here, I can say git merge A, B, C, D, E, and Git will merge all of them into one child commit. That is sometimes, not sometimes. Sometimes Git will leverage what is known as the octo-merge strategy. Anyone use GitHub in this room? Any GitHub users? So if you've seen the octocat, that's where it comes from. The octocat is the octo-merge, essentially. Or at least that's my belief, where they got the octo-merge from. But this is a child with 2 parents. But there's one step missing. Git will first create the child commit that represents the marriage of those two commits. It will then move master up there. Means the person who's doing the proposal automatically gets bumped to the child commit. So this will be the state of affairs after you merge these two branches. Bear in mind, new feature does not move. New feature still points to the commit it was on before the merge happened. Does that make sense? Now, merge is usually easy for most people coming from other source control systems because we always do merges. It's a very common practice. But one thing I do like to remind people is you should always use merge for public history. And I'll come back to this in a second as to why this is important. How many people have done a rebase in Git? Any rebase fans? I'm a huge fan, huge. If I ever meet the man who came up with rebase or the lady who came up with rebase, I will kiss their hands. It is the Swiss Army knife in Git. You can do anything with rebase. Rebase and filter branch are primarily the Swiss Army knives in Git. So let's see what rebase is all about. Because the problem with rebase is some people don't understand rebase. Some people don't understand why it's there when you already have merge. What's the difference between rebase and merge? If you Google Git rebase versus merge, it's like the flame wars that went on between Emacs and VI. Some people say always merge. Some people say always rebase. They're two different tools. And you should pick them after you understand how the DAG will look. You will better make a choice as to whether you should be rebasing or merging. Rebase is relocation. You're moving to a new house. This is my state of affairs just like last time, except in this case, what branch am I on? New feature. And I'm going to say, I want to be that jumped too quickly. I want to be relocated where master is relocated. So let's take a quick step back over here. This commit's parent was this guy. Both of these commits shared the same parent, which is not important, but the point is still, this guy's parent is him, this guy's parent is him. When I say I want to be relocated, what I want is to change the history of this commit, and instead of saying I was born out of him, I want to say I was born out of him. Relocate me to a new commit on the tree. So if I were to do at this point a git rebase master, Git literally takes this commit, tears it out from the tree, and slaps it on top of this guy. Now, let's take a quick example here. Over here, I had one file called 1.txt, right? Here I add a second file called 2.txt. How many files do I have in this commit? 2 files, 1 and 2, right? Remember, Git stores the entire tree every single time. Let's say over here I added a.txt. So how many files are there in that commit? 3, a, 2, 1. Let's say here I added a file called b.txt. How many files do I have? 3, b, 2, 1. If I merge these two commits, what will the merged child look like? You'll have 4 files in it. A, B, 1, 2, right? Now, instead of creating this commit after this commit, what if I had created this commit after this commit, like this? What would this commit consist of? Remember, I had b.txt over here. What would this commit look like? Still 4 files, right? 1, 2, A, B. What rebase does is it rewrites history. Basically, I'm pretending this commit didn't happen after this guy. It happened after this guy. I'm tearing it out from the tree and slapping it somewhere else. Relocate me from this parent to another parent. Does that make sense? Rebase is hard to understand just because this concept is hard to understand. Just one second. Yes, sir?
So it's literally not just changing the parent pointer. It's actually changing what is stored, zipped up into that init for new feature. Like it's changing the actual contents of that.
It cannot change the contents. If here I added b.txt, that b.txt still exists over here. Okay. The problem is that instead of now, when I started this commit, I had 1, 2, and I added b, right? Now, if I pretend this commit happened after this commit, what's my baseline? It's 1, 2, a.txt. So this commit now has 4 files in it. So in a way, and actually that's a good point, the reason why I changed the colors from green to yellow is it does rewrite the commit. It has to rewrite the commit because the tree in this case changed. Right? Now, let's take one more step. Even if nothing changed, what changed? Timestamp. It has to still rewrite the commit. Miss?
Wouldn't I end up with the same situation if I took a different version feature?
Yeah. Exactly the same benefit.
So the advantage of rebasing that is what?
Notice this little triangle that you see here, where two guys come together. When you have a tree that's got 100 branches with multiple triangles all over the place, reading history becomes a nightmare. It's a good question, though, by the way. That's the reason why rebase exists. To a large extent, why rebase exists is, notice the history now. It's one straight line, very easy to read, right? That's why rebase exists. So rebase and merge fundamentally do the same thing. The end result will be the same. Just like in a merge that you can get merge conflicts, you can get merge conflicts in a rebase because it essentially is replaying those commits on top of something that already happened. If I change a file on this side and I change the same file on this side and I merge the two, I'll get a merge conflict. If I change the file, I change the same file, and I pretend this file happened after this file, change, what happens? You still get a merge conflict. You're still going to get the exact same behavior, but the tree looks different. In one case, you get this funky triangle. In the other case, you get a straight line. Now, earlier I said always use Git for public commits. Always use rebase for your private commits. What I mean by private commits are this commit cannot be seen by anybody else before you rebase it. If you've pushed it up to GitHub or you've pushed it up to some Git server, you cannot rebase the commit. Or let me rephrase that. You should not rebase that commit. Why? You and I are working. This is the tree at a certain point in time. I push up to GitHub, right? So we get this 4 commits up in GitHub. You do a pull. You get all 4 commits. You are a diligent developer, right? You start hacking away on this branch. So you have a commit after this, a commit after that, a commit after that. I, in my infinite wisdom, decide I went to that conference and I learned about rebase. Let's try it over here. So I rebase that commit. What happened to the commit that was existing? It just went away. Git will say, you don't need that commit. I'm going to throw it away. I push this up. You pull. What happened to the commit that was your work was based off of? It's gone. That commit no longer exists in the tree. I just screwed you over. Never, ever, ever, ever rebase a public commit. You have to be very careful when you rebase. If in doubt, don't do it. Right? So if you have a private feature branch, rebase it before you merge back into master. You get a nice straight line. But if you're working on a shared branch with you and your colleagues, always merge and then push up. Because if you notice the merge, no commit disappears. Right? Every commit is still in the tree except you get new commits. So no one's work gets affected. Does that make sense? Excellent. So rebase is relocation, merge is marriage. And with that, that's all I had. So any questions? Yes, sir.
Would there be a reason to use rebase even in a private branch?
So the question is, will there be ever a reason to use rebase in a private branch? I usually like it because the way you normally catch up with master, right? So master is marching along underneath you. Your colleagues are pushing all to master, right? They have their feature branches. They merge to master. They push to GitHub. You pull from GitHub. Master is marching underneath you. You're working on your little topic branch, right? And you're ready to come back into master. Most people don't merge your local branch immediately into master, because if you get a merge conflict, you're going to resolve that merge conflict on master. The normal tendency is first go to your branch, pull on origin master, and then merge master into you. So any conflicts are resolved locally on your branch, then go back to master and merge the other way, right? So there what happens, you get master going up here. This is your branch over here. You first see a triangle come this way on this side, and then you did I lose my voice? No. And then you see another triangle going the other way. So it becomes this weird pattern of merging. So what I prefer to do is my branch is over here. First, rebase on top of master, so one straight line. And then when you come back into master, it's a fast-forward merge. So your history in your local tree is one straight line. When you push that up, people don't even see that little, they just see a straight line. So your history is very much straight. You're still going to get triangles because the minute I touch public branches, I have to merge. But the lines are a lot more straighter. But yes, you're right. It's a choice thing. There's another thing called Git Rebase Interactive, which is awesome, but we'll talk about that some other time. Yep. Git actually has a garbage collection process that goes through that directory, the objects directory, every once in a while, and checks every commit and says, do you have anybody pointing to you? If there's no one pointing to you, throw away the commit. Furthermore, if I take this branch out, even if this node exists, when I push up to GitHub or Git server or whatever, Git will not push this commit because there's no hard references to it. You can't get to it. Git says, I'm not going to even push it up there. So the only tree you will see up there is these 3 dots. Does that answer your question? If you've merged, yeah. So if you've done, oh, sorry, this is a rebase. So if you've merged, you throw away the post-it note, this will still remain. You will still see this on the Git server because there is another commit. This guy points to 2 parents. So both parents will show up. Everybody else will see the 2 parents. Does that make sense? But the post-it note goes away. And that's why I like to call it a post-it note. They are literally that expendable. Anybody else? Yes, sir.
How does Git track which files have been added to the index, but doesn't have any yet?
Oh, that's a slightly lengthier discussion. It's a good question, though. It's a good question. A lot of time, I mean, one way to think about it is there is actually a staging area in Git that it maintains. So every time you do a git add, it knows which files showed up there recently. You can even force a file to be added to the staging area with no changes. The same thing. There's a pointer in that staging area that points to that file. And it takes all those files, does the calculations we talked about, calculates the blobs, calculates the trees, calculates the commits. But it's a longer discussion. All right. Well, I know I had the first or second session, I think, after the keynote. So I do hope you enjoy the conference. I was told that you have comment cards to fill out. So please, as a speaker, I know I appreciate the feedback. So if you have anything to say, please fill out your comment cards. And I'm hoping we get a look at them later. I don't know how this works, but I'm sure we'll take a look at them later. Oh, survey. Even better. Even better. Oh, OK, so there's an online survey. Please fill it out with your comments. I would love to hear from you. Otherwise, I'll hopefully see you in the next hour or two. Enjoy the conference. Thanks for coming in.